We'll continue with that only, and we say what are the variety of way clippers are arranged. So some, discussion quite almost with full detail has been presented to you by Professor Sen Gupta on last Friday. And yes, I will start from that particular point because he has given everything that much in detail that going to that once again will be your repetition. So I will do the same thing. I'll bring some other aspect of the diode characteristics in your clipper circuits. And finally, I'll go to the transistor used as a clipper. Can the transistor clip both the sides? We have to see that. You have designed the circuit. It's not simple, straightforward. So these things we will discuss today. So I think others will be joining in the meantime. I need the handler, Professor Gupta, to go for the presentation. Professor Sen Gupta, handler is not coming to me for presentation.
Yes, sir. Let me give it.
You see that? If there is any question, any doubt, students are free to ask me. It will be the same thing, but I will be bringing some more parameters into consideration. Okay? So, still it's not coming. Now it has come. Yeah, I can see. Yeah, I can see that. I'll take the presentation handler now. I'll start with that. So single, clipping that you have seen. Now, I will start with the dual clipping, and anyway, any one part will become a single clipping automatically. So we'll go by that. Let us see what are the things that we need in this thing. Okay. Okay, so you can see the slide. I have drawn a small line there. I have drawn a circle there. You can see that. Okay. I hope you can see that. Now I'm talking about the clipper. There are two different requirements to have a clipper. One clipper is the sinusoidal signal. Here, if I use the clipper, I may like to clip in one direction, positive half or negative half or both. I'm considering the general case so that I want this portion to be clipped. Let me take some other color that is better. Color 2. Color 1, color 2 is red, I think. Add group to quick access toolbar. Is it okay? No, it is not taking. Why? I'm taking home. Color 2, I have to choose from here. What happened? No. Why is something wrong this time with mine?
Sir, color 2 is white. That's why it is not coming.
Now, color 2, I have to change. Color 2, how to change the color 2? I want to make a red.
Color 2, then you press that one. Yes, you now press.
The red has not gone there. Add group to quick access toolbar.
No, left, and it is not coming.
Even the green is also not going there. Earlier it was coming. I don't know what has happened. Students can help me there. Color 2 green has come now. Okay. Now green has come. I choose the color 2. Color 2 green has come. And then nothing is coming. Why? I choose color 2. Oh no. Green has come here. Okay, let me choose.
Sir, you use mouse to select color 2.
Might be then the region.
My select mouse.
I'm selecting this. Still black is coming. I don't know what has happened to this selections now.
No, now it has come. No?
Green has come, but green is not picking up on my pen.
Sir, in color 1, select the green color.
Color 1, I select what? Color 1, I can make it black. This black is already there. Color 1,
Yes,
I
I
can
change it to
change.
green.
How to change? Add quick access one there. Minimize
Sir,
the
using
ribbons
the
quicker.
mouse.
Huh? I'm using the mouse only. So quick access, minimize. I'm using this. No, it is going out of there.
It is getting minimized. So just uncheck that button, minimized.
Uncheck that button, minimize.
Once you click that, you click that one, you see that yes. Now
Minimize. How can it change like that? Is it not? It's
then
not taking.
it will
Not.
take.
Oh, edit color. Let me change from here. Oh, sorry.
No, it's okay. Now you can do it. No issue.
I've chosen. Okay. Oh no, still. It's very funny.
Change color 1 to green. There it is.
Change color 1 to green. How can I change color 1 to green now?
Now you press green.
Now it has become green now. Both have become green. Oh, now it is okay. Color 2 is not the thing. Okay. Okay, fine. Let it be. Okay, so now what I want to do, that green color, I want this to be clipped. So my signal will be coming something like that. Like that. And here I want to be clipped like this. Sorry, straight line this. Okay. So here it comes like this, it comes like this. Now, this I'm calling voltage as VR1. Okay. This voltage, where it is clipped, I call as VR2. I am considering both of them are positive. Reference voltage 1, reference voltage 2, I am considering both are positive, but signal I am taking here is going positive and negative both. You can put VR1, VR2 as a negative magnitude, you will get the answer automatically. So here I am considering both of them are positive. Okay? VR1 is positive, VR2 is also positive, but VR1 is greater than VR2. Lower portion clipped is VR2, upper portion clipped is VR1. That's what I am going to get a circuit for it. Edit the color. I think I have to go by that. Black color. Okay. Add to custom colors. What about? Okay. Oh, now it's okay. Fine. So now a circuit for this. Hossein Gupta has given you a circuit for this. This I want to make, isn't it? What way this voltage input-output relationship holds here? This is my VI, this is my V0. Now I want to plot this is my voltage V0 with respect to my voltage VI. So what I am getting? That when it is clipped, it becomes constant. It becomes constant. If it is negative, I'm drawing like negative to considering this as a 0, but for your reference sake, I'm considering both are positive, and I write the values like that. So you may consider that 0 is somewhere here. But anyway, in between, it will be coming like that. This is a circuit that we want to get. And Professor Sen Gupta gave a circuit. Remember that? It was like this. A voltage was coming like this. Here there was a positive voltage. There is a resistance here. Single resistance in making the parallel combination. This is my VR1. This is my diode D1. And for VR2, diode is inverted. Here it is negative voltage. I call it as VR2. And this is my output. So this you remember, one by one it was considered, and he has shown that whatever it is clipping. Here what happens, if Vi is greater than VR1. VR1 is greater than VR2, remember. So if it is greater than VR1, this diode gets forward bias and this VR1 appears here. So this one is your, this V0 will be something when Vi goes VR1 plus V gamma, cut-in voltage, plus V gamma, sorry. When this Vi becomes VR1 plus V gamma, it will fire and it will become this point, and this is also same thing, VR1 plus V gamma. I have not considered diode resistance. DC resistance is R. Okay, diode is ideal. When it is forward bias, resistance is 0, reverse bias resistance is infinite in both the cases. So in the lower case, what happens? When Vi is less than VR2, less than VR2, okay? Assume that it is clipping in both the sides, I think that is better. If it is less than VR2, then this diode becomes forward bias and output is negative VR2. Consider bidirectional, that is better. So here what happens? This voltage is VR2 plus V gamma. And this one is also VR2 plus V gamma. In fact, it is V gamma 2 here, it is V gamma 2 here, it is V gamma 1 here, gamma 1 here, V gamma 1 here. So this thing is VR1 plus V gamma 1. Diode cut-in voltage are not the same. So it is V gamma 1, V gamma 2, it comes like that. Is the model clear? Okay, so that way, two-way cutting clipping of the sinusoidal signal that we have seen. Your voltage goes like that, output shape of the voltage looks like this. Now, I am considering this diode resistance, D1 has got RF forward bias and RR for the reverse bias, and RF1 and RR1, and D2 has got same thing. Somebody raised a question, what a numerical will be solved? Now you will be able to solve the numerical when the values will be changing. RF2 and RR2. So D1 is having this resistance, D2 is having this resistance is R as such. It was not taken into consideration because diode as ideal, no current was, no voltage drop was taking place across this R. So Pi, nothing was subtracted from there. Okay, because 0 by something becomes output becoming a 0 itself. So ideal case, it was not your this thing. If it is, forward bias, this VR was coming there, the cut-in voltage. So your input was constant there. Now this is the case. So what I'm going to get here is, this is the one I'm plotting this like that. Same thing, relationship. Accordingly, this shape will be changing. Green color shape will be modified, will be changing according to that. So here what will happen? it will be going like this. It will not be constant, it will be going something like this. Here it will be going something like this. This and this may not be parallel. That's what I'm trying to discuss here today. This is my V naught, the V naught, and this is my Vi. Okay, now what is this slope? This slope. When is this slope? When this was your V gamma 1, it's VR1 plus V gamma 1. Is it okay? All students agree to that? At this point it was there, and then what happens? When it becomes greater than that, it becomes forward bias. So voltage, I said V gamma VR1 appears at the output, but not. What is appearing? What voltage is appearing here? It will be VR1 plus or minus. Check it. VR1 is appearing here. Then drop across this D1, that is also getting added to VR1. Across this is becoming your less than that, sorry, greater than that, so it's forward bias. So this resistance will be RF1 divided by R plus RF1. Okay? This is the current flowing through the diode multiplied by which voltage? Vi, because Vi becoming greater than V gamma, VR1 plus V gamma. So Vi minus VR1 minus V gamma 1. Is it okay now? VR1 minus becomes a VR1, when negative I take outside, it is like that. So RF1 by R plus RF1, suppose this I make, this is very small. RF1, if it is very small, it can be neglected. RF1 by R plus RF1 will become close to 0. So it will be a VR1. Otherwise, what is the slope of this line? This is my V naught. This is my V naught. So you have to find V naught by Vi equal to how much? The VR1, again RF1 into VR1 plus V gamma will appear here. Okay? And you solve that. So your V naught 1 will be appearing in terms of this Vi. So V naught by Vi will be this slope. Shall I do it? You will be able to try during your homework or something like that. I have given the expression here. V naught equal to VR1 plus this thing. Approximately it will be equal to VR1. Okay, but I want to see the Vi dependency over here. Then this V naught by Vi I have to find out. In terms of VR1 and RF1 and R, this ratio will appear. It can be solved. I think you know better how to solve this. You have to separate Vi1 from this side, divide both the sides by Vi1. So VR1 by Vi1 will also appear. So if the Vi is increasing, the slope is also increasing by that. So VR1 by V gamma 1 will also be getting divided by Vi. But if it is considered that forward bias resistance is close to 0, then 0 divided by R will become 0 and this can be neglected. Is it okay? So this Vi can plot like that. I can find the source slope like this. It will be Coming to the negative direction, it is VR2 plus V gamma, this thing. After that, it in negative direction, it is increasing. So what is V naught there? I'll take help of the green color now. Edit color. Here, where is gone? Here. Okay. So lower portion here, this one now I'm writing. It's gone there. Not seen. This portion I'm talking. Okay. This one will be hard. VR2 is larger than VI. Okay. In the negative direction, V are increasing. So it will be your VI will be negative minus VR2. It will become positive. This minus this. Okay. VR2 minus V gamma again. V gamma 2. Again RF2 divided by R plus RF2. Again RF2 is small, it will become your plus is there. Plus BR2 plus B gamma. BR2 plus B gamma coming here also. B gamma is coming here also. B gamma 1 is coming. Here B gamma 2 coming here. So if it is very small, you are left with this, and that's how the clipper circuit is working. Now question comes, what is the slope of this? This is a straight line. Okay. Where is the pen gone? I don't know. With pen here. Here I'm talking this thing. Positive direction. What is going to be here? VI is positive. Okay. Increasing. And this diode D1 is reverse biased. If it is reverse biased, what is this slope? Yeah. This slope will be, this is my VI. Okay. Reverse biased, your R is there. So it is VI. Can't proceed. You can't see that. Yeah. VI is there. Let me take another page. I think I should have gone for that slide itself. That is better. Anyway, let me take the another page. Oh. Can you hear me? Am I audible? Sen Gupta?
Yes,
okay?
sir.
Okay, fine. Now I'm doing the same thing, sorry. I'm doing the same thing in this range now. Assuming this has gone like this has gone like this, I'm here now. So this was my VR1 plus V gamma. This was my VR2, sorry, VR1 itself. VR2. VR2, it was negative direction. Minus V gamma, so it's plus here. Here is a negative direction here, like that. It was coming like this. These points were like this. Okay, I'm interested in this thing. So what happens here? Diode is reverse biased. Okay, so here VI minus VR2 VR1 VR1 cut-in voltage is not coming at all. There is no cut-in voltage coming. VI minus VR1 divided by R plus RR into RR. That is the voltage V naught. So this becomes my V naught. V naught by VI I have to compute here. V naught by VI equal to how much I have to compute there by substituting these values like that. VR, RR, etc. Substitute. V naught by VI I can find out. It will be a linear relationship. I can get that. Okay. If diode is ideal, RR becomes infinite. Okay. So this becomes equal to RR divided by RR because R becomes very small compared to reverse bias resistance, and you are left with V naught equal to VI minus VR1. No, it will be 0 in that case. VR1 will not appear because RR becomes infinite. So it is something like that. Just see. You have got VI by, here is your RR. Here is R plus RR minus VR into RR divided by R plus RR. Okay, so VR is appearing there, but it is not taking part in this one. So that means this is almost becomes equal to V, this is my V naught. Will be having a slope something RR by R plus RR like that. This is offset. This is the offset on the y-axis. It will be going like that. It may not pass through the exactly 0 point, so that you can check according to the values. So V naught here will be like that, and here it will be same thing. It was your RR1, VR1, RR1, something like that. In this case, it will be your VI divided by RR2 of the second diode divided by R plus RR2 minus VR2 into RR2 divided by R plus RR2. So this becomes offset, and this is your slope RR2 by R plus RR2. If it is very large, slope becomes your 1. So that's why we approximate it by slope as 1. This is also putting as a constant, that means slope becomes 0 because your forward resistance is very, very small. So almost touching the 0, so it becomes your 0 slope. So that's how it is working. Could I explain what way you will be computing the exact numerical values over there? Or any student has got any specific question, reservation or so? So these exact values, depending on the practical diode that you are choosing, it goes by that. I'm coming to the second characteristic of your clipper. These are on head no question. I'm going to the second one now. Okay, fine. I'm here. Second clipper we need is, this is my sinusoidal signal. Sine, cosine, whatever thing you want, you can assume like this. This is my T, this is my VI. What my V naught is doing here is, where is the color here? Green I'm taking. Okay, fine. Here what I am doing, I am taking this portion. It is coming like this. Then I want to take this portion. It is coming like this. See, there is some kind of conceptual gap here. Should not have in your mind. It is something coming like that. If it's a single one, that's fine. You have seen here it is clamped here. Okay, it is clipped here. Only this portion is coming. Only this portion is coming. One way clipping is fine, but if I want to go for two-way clipping, what I am getting? It is something coming like this. I am here. This portion I want to drop. Okay. Is it possible to drop this portion? It has to be a single valued function. Okay. So here it's a kind of raising the DC and then getting this. It will not be possible. So what will happen? It will come to some reference here. It will come to some reference here. So instead of getting this only portion this much, I am getting from here to here vertical rise. Here it is negligible 0. Here to here also it is 0. Similarly, here I am getting something. Here it is 0. Here I am getting something. This side becomes 0. I am getting this voltage. So what I am getting is this thing coming to 0. Here I am getting, starting from this reference point, it is coming here and then vertically falling to that 0. So this kind of signal you will be getting when you clip only this portion. So only small portion of the sinusoidal signal will be appearing. Only small portion of the sinusoidal signal will be appearing like that. If only one clipper I am using, it will be coming like that. It will be something like that. It will be coming something like that. If I am using two-way clipper, the way it appears, can I get this thing? At this particular time, I am having one value, I am having one more value, second value. Here I am having one value, I am having second value also. So a particular time instant, the function is having two values, this output you cannot get. So when you make two-sided clipping, you will get this. Professor Gupta has explained one-sided clipping here. When you make two-sided clipping, it will be coming here. What will be a reference voltage? I am coming to that. Is the point clear now? So in two-side clipping you are doing, there will be a reference here. With respect to reference, you will be getting the sinusoidal shape. But here it will be vertically falling to 0 at the two edges. Falling to 0, that sinusoidal shape will be there. And then at the receiver, you have to do some kind of signal processing to extract this, removing this kind of a square wave kind of pulses, not a square wave, remove this kind of pulses, positive and negative amplitudes. From there by some kind of subtraction or so. But in the clipping circuit, we are going to get like this. Why it is so? Remember, I think I should choose a black one. Is it black one taken? Now black is taken. Good. So you remember, Professor Gupta explained, for this kind of clipping in one direction, it was coming like this. It was coming like this. And yeah. Remember, in the previous clipping, this diode was inverted. Okay, so this is my VR1. VR1 will give me this one, this level. This is my VR1. Now the second direction also I want to clip. This diode also will be inverted, but battery supply is same as previous one. Here also it is negative, it is positive. There this diode is inverted, battery are remaining same thing, positive and negative. Here diode is inverted, battery remains negative here, like that. So this will give me this kind of cutoff. Now when I take the output here, the both of them are joined. So output cannot be two valued at any time instant. Okay, so this is my VR2, and this is my D2, this is my D1, and this is my R. So this portion, this sinusoidal portion that is coming here also, that will not be a pure sinusoidal if the diodes are not ideal. If they are ideal, it is pure sinusoidal. This shaded portion is removed from there. It is a pure sinusoidal and it is falling vertically to this reference voltage. Here what happens? What way this sinusoidal shape is changing? Okay, so my V naught is, if it is, what happens? Less, if it is greater than VR1, if this input is greater than VR1, that means diode becomes reverse bias. Diode becomes reverse biased. Okay, so my V1 comes here, same thing appears there. So what is this output now? Okay, that output will be VR1 plus voltage across the diode, that is reverse bias. Okay, VR1 plus Vi minus VR1 divided by R plus RR1, reverse bias, and in the numerator it will be once again multiplied by RR1. So I am putting a division here, RR1. If RR1 is very large, reverse bias condition, this will become your 1. So VR1 minus Vi minus VR1 becomes your Vi. So V naught becomes equal to Vi, no attenuation. But if RR1 is not infinite compared to my R, then this will be the factor coming in the denominator. Or this RR1 goes in the numerator, that's how it is changing. So V naught by Vi will be modified with a slope, with a constant. That constant will multiply the sinusoidal shape, and shape will be changing according to that. Is it okay? Same thing happen negative direction. Here V naught will be VR2 plus, here Vi becomes a negative, and that is, so here it will becoming VR2 and negative minus Vi minus VR2 divided by R plus RR2 divided by RR2. Now, what is the reference voltage here? When this shape is not conducting, when both the diodes are not reverse biased. One of them is, if it is here, there can be only one of them as a forward bias. Both of them can also be forward bias. If negative, this voltage VR2 is greater than, in negative direction, this is forward bias. If it is smaller than VR1, so between VR1 and VR2, both of them are forward biased. Between VR1 and VR2, both the diodes, Vi is less than VR1 and Vi is greater than Vr2 in negative direction, both the diodes are forward bias. So what is my reference? V naught. I'm writing the result here. You discuss your divided by 2. So your this reference point here that I have drawn there earlier, where is that? That is gone, or that is gone. When I have drawn like this, I have taken like this, then it was coming to this point, then I took like this. This was the sinusoidal one, and this reference point was your 0 was somewhere here. So this was Vr1 plus Vr2 divided by 2. It can change also. If the capacitance of the diode is different, it will change. How does it come? Look at this. What is the charge stored in the capacitance of the diode? Okay, across the diode there is some voltage drop that is according to Vr2. Okay, so if it is forward bias, both of them are forward bias in that case. If it is forward bias, this one will be Vr1 plus V gamma coming here, Vr2 negative direction, Vr2 plus V gamma with a negative direction is appearing at this point. So during this time, how much is the charge stored in this diode? Okay, so across the not the diode, I'm sorry, this battery. How much is the charge stored in this battery? How much is the charge stored in this battery? And when both of them are working together, these capacitances of the batteries, the charge will get added by conservation of the charge. Okay, so what is happening? Suppose it is C1. So C1 into Vr1 is the charge in this one plus C2 into Vr2 is charge in this one. So this becomes my charge Q. Then this divided by, suppose I want to find the charge voltage. So V equal to what? Q by C, and that C will be 2 C's parallel, C1 plus C2. So two batteries will be considered parallel combination. That total capacity is C1 plus C2. So C1 into Vr1 plus C2 into Vr2 divided by C1 plus C2. Suppose C1 and C2 are equal, then what is going to happen? It will become that is equal to C. Here is your Vr1 plus Vr2. Both are identical batteries but different voltage values. Capacitance is fixed, charge is changing. This one will be your 2C. This C and C cancels, it becomes Vr1 plus Vr2 divided by 2. So this reference point here will be Vr1 plus Vr2 divided by 2. That will be, that's always, it may not be 0. Suppose Vr1 and Vr2 are equal, one is positive, one is negative, it will be a 0 volt. But suppose Vr1 is 3 and Vr2 is minus 1, okay, then it will not be 0, it will be some other value over there. So that's how this threshold will be changing and will be getting a shape, something like that. If you want to get this, only one at a time that you have to do. So either you get this or you get this, but if you want to get both of them combined, the shape will be something like that. And this threshold from where this vertical fall to that threshold will be coming. or that sinusoidal shape, that tip, that will be calculated according to that. So two batteries are just like capacitors. Capacitors are charged that become a battery. So that's what you already know about this thing. So this clipper I have completed. Another one is transistor as a clipper. So transistor will clip in only one direction. Okay, like that. Maybe I will be discussing that again. Transistor will be clipping in only one direction. That is your V naught is this one. I'm plotting like this. Vi was, let us say, sinusoidal signal like that. Okay. So here again, I take color. It will not select that. Really, it's okay. It has taken now. Now it's okay. So V naught, I'm putting like that. It will be inverted first of all. Okay. So the transistor will clip sinusoidal signal. It is inverted. It comes like this. It comes like this. It comes like this. That will be my V naught. And this was my Vi. I'll come to this maybe in the next lecture or so, because right now, unless you have got full clarity, there is no point in moving to the transistor. You already know, but anyway, it's coming as a kind of amplification and voltage inversion. So like that. So this V naught will be something like that. It will be clipping here. Now, can I clip it in both the directions like this? Question mark. It is not straightforward. You have to design a circuit. There I have made a threshold has come. There the two are working, but here it is not. So there is a question mark here. Now question. Any question here? So clipper I have completed. Transistor or two, they will go to a clamping circuit. Okay. So good day. See you again.
Yes, sir.
Thank you.